Thank you very much. Thank you for the invitation. I'm not sure if my voice comes through the Zoom, but I'll try to speak as loud as possible. So thanks for the invitation again. It's great to be back at McGill. We had great years here, really fun and exciting times in the 80s. So I'm going to give my talk in three parts. First is I'm going to try to motivate the research on time delay systems for those of you who are not familiar with it. Then we'll talk about stability and strong stabilization. What do I mean by feedback system stability and strong stabilization? I assume everyone here is expert on control systems.
Recording in progress.
And okay, so you okay. No, mute the mic.
You have to mute your speaker. Carry on.
Okay. So I will talk about Nevanina peak interpolation, which has been used in the old days of robust control, and how it is used to solve stability and strong stabilization problems. And in the second part, I will motivate the strong stabilization problem, and then illustrate interpolation methods for that. And in part three, we'll just solve the main problem, time delay systems, strong stabilization. And I'll end with some open research problems that are related. So time delays are seen in physical world all over the place. You know, they come through processing delays, transmission delays, human-machine interaction, human reaction time is slow. Non-collocation of actuation and sensing in physical systems. And they appear in many biological, chemical, physical systems represented by typically partial differential equations. One typical example is a networked control system where you have a physical plant here, which contains the process, actuator, and sensor. And far away, there is a controller. And the communication between these two are done through communication networks. So you send the command signal from the controller, and it gets to the physical system through the communication network. So this signal U is not exactly equal to UC. And the simplest model of this transmission is a delay, pure time delay. There are, of course, other issues involved with the communication networks. For example, there may be a jitter in the delay, there may be packet losses, quantization, etc., etc. Okay, some network control systems, examples, from different applications. I'm just going to skip this since you are all familiar with all these kind of things. Gene regulatory networks also contain time delays. If you model the cell population dynamics in leukemia, for example, there's a famous time delay system model for it. In fact, the very first original paper on biological cell population dynamics came out of McGill University. McKay, I don't know if you know him, presented that. So, okay, let's put everything into perspective. Okay, what do I mean a system and how I represent the system? So these are very basics of systems and control theory. So let's say you have a plant. I assume that the plants that we are dealing with are linear time invariant. Therefore, the input-output relationship can be represented by the transfer function, okay? And stability, I define it to be L2 L2 norm, L2 induced norm, boundedness of the L2 induced norm. So that brings us to the H infinity stability. That is the transfer function for a system to be stable, the transfer function must be in H infinity. Bounded analytic functions in the right half plane. And the operator norm is the H infinity norm, actually. Okay. So in particular, this means that the plant should not have poles in the right half plane. But if you have time delay systems and infinitely many poles appear, and there are some other technical details. Okay. So time delay. So if your output is just a constant delayed version of the input, the transfer function is e to the minus hs, Laplace transform property. Okay, so in this case, you see that an irrational transfer function appears. Okay, so for finite dimensional systems, the transfer functions are rational. Okay, so you have finitely many poles and poles and zeros. And for infinite dimensional systems, you have infinitely many. You may have infinitely many poles and zeros. Okay, and throughout the talk, I will mention something called inner function. So we say that a stable transfer function, so stability in the sense of H infinity, is inner if its magnitude on the imaginary axis is 1 almost everywhere. And then there is another thing which I use later on, is the small gain theorem. So George is looking at us. He's checking. His picture is over there. So if you have a feedback connection like this, where G is stable and delta is stable, and then this feedback connection is stable for all delta stable, such that the infinity norm of G times delta is less than 1. So that's called the small gain theorem. Okay. Okay. Example of a infinite dimensional or time delay system transfer function. So you're trying to balance a stick in your hand. Okay. So let's take something here. This one. Okay. You're balancing this. So what you do is you look at with your eyes where the current position is. You get feedback from it, and then you process it in your brain, and then do actuation through your hand. Okay, so human reaction time is the delay, and then the rest is the physical property of an inverted pendulum. It's an unstable system because it has a pole in the right half plane. Okay, so I already talked about the feedback system connection, but again, stability of the feedback system is equivalent to having all these three transfer functions in H infinity: sensitivity, controller time sensitivity, and plant time sensitivity. So obviously, when sensitivity is stable, then 1 minus sensitivity is the complementary sensitivity. So that is the transfer function classical from reference to the output. So it's already stable. But then you also need controller time sensitivity and plant time sensitivity also in H infinity, because if one of them is unstable, then one of the transfer functions will be unstable. So usually when we teach undergraduates, we skip this thing, okay? But it should be mentioned because that is equivalent to having no unstable pole zero cancellation in the product when you take plant times controller. So if plant has S minus 1 over S minus 1 over S, let's say, so you cannot use K over S minus 1 in the controller. You cannot cancel the 0 with a pole in the controller, okay, and vice versa. Okay, so that is the feedback system stability. All transfer functions must be in H infinity. So that's equivalent to having one of the transfer functions, let's say S in H infinity, plus no unstable pole zero cancellation. Strong stability, which is the subject of today's talk, is feedback system stability by using stable controllers only. Okay, so that's the strong stability problem. And later on, I will motivate why we are interested in this. Okay, so we have 4 problems of interest. One, S0, feedback system stability. The second problem is SS0, strong stabilization problem, which I have already defined them. And then there is also a weighted sensitivity minimization problem, which is feedback system stability plus the minimization, H infinity norm minimization of the weighted sensitivity. Okay? And the associated strong version of this problem is weighted sensitivity minimization with strong destabilizing controls. Okay, so there are 4 problems that will be of interest to us later on. Okay? So feedback system stabilization can be done by analytic interpolation. Let's say you have a plant, given plant, and you want to find a controller to stabilize the feedback system. So for the sake of argument, assume that P is rational and its poles and zeros in the extended closed right half plane are like this, given here. So there are total n poles and zeros in the extended closed right half plane, and assume that they are distinct, and then feedback system stability is equivalent to finding a function S, sensitivity function, which is stable, such that these S takes certain values at the right half plane, poles and zeros. So these interpolation conditions actually correspond to no unstable pole zero cancellation condition in the Planck times controller expression. Okay? Because you see sensitivity becomes 0 at the unstable poles of the plant, and sensitivity becomes 1 at the unstable zeros of the plant. Okay? So that there is no unstable pole zero cancellation. And then, so basically, this problem is equivalent to finding, given some points in the right half plane and their corresponding values, find a stable transfer function which does this job. So this is the Lagrange interpolation problem, and it's relatively easy to solve. Then you construct the controller from the sensitivity that you have constructed this way. Okay, so this is something that appeared in the 1980s and forgotten afterwards. This is not what people do usually. Okay. Sensitivity minimization is equivalent to Nevanlina peak interpolation. So that is, you have some points in the right half plane and their corresponding values. So you need to find an interpolating function, stable, and you want to have the smallest norm possible, H infinity norm possible for this. Okay, historically speaking, Nevanlina peak solution goes back to an algorithm which appears in Walsh's book. It's a sequential algorithm. Okay, so you first find the first interpolating function, then use it for the second one and the third one, and so on and so forth. You continue like this. Okay, and then this algorithm has been used in robust control theory first by my PhD advisor, Alan Tannenbaum, in 1980. Then Bill Helton used it in circuit theory literature. And then Zames and Francis used to solve H infinity control problem. And Kargonecker and Tannenbaum later on used to solve other stability margin optimization problem. The sequential Nevalin-Epic algorithm is rather cumbersome to implement, actually, but there is an easy one-shot solution in the latest books. Boll, Gohberg, Rodman's book have one, and our book with Foyash, we also included a one-shot solution. But the simplest solution, in my point of view, for the optimal interpolant is in our paper here. I'm not going to spend much time on this. It's just that there exists a simple one-shot solution. So optimal interpolant is an inner function which can be constructed by finding the eigenvalues and eigenvectors of a certain matrix here, this matrix, okay? Let me skip this. Now, so far, problem S0 and S1. So stability and sensitivity minimization we discussed. Now, how about strong stability? Strong stability is equivalent to construction of a unit in H infinity which satisfies certain interpolation conditions. Now, what do I mean by a unit in H infinity? U is a unit in H infinity if it is in H infinity and its inverse is also in H infinity. Okay, so if we can start with a coprime factorization of the plant in this form, n over d, where n and d are coprime in H infinity, and assume that the controller is Q in H infinity, then the feedback system is stable if and only if this U is unit in H infinity. And this U, you see when n becomes 0 at a point z, let's say, then U must be equal to d of z. So these are the interpolation conditions for the unit construction, okay? So in this case, once you constructed such a U, sensitivity function is this, and controller is written in this form, okay? One other thing I should mention for the sensitivity minimization problem, when the plant is infinite dimensional, when n is contains delays, for example, Nevalin-Epic interpolation is not really helpful. So you have to go to other extensions of the interpolations. And for the sensitivity minimization for strongly stabilizing controllers, we'll come to this problem later. Okay. Now, why do we do strong stabilization? Okay. Again, let's recall again, feedback system, but this time I put the sensor here just to argue one of the reasons for strong stabilization. So P times H is my plant, as in the previous function, the slides. Okay, so one important thing is that unstable plants are difficult to control. So if P and H are stable, then choosing C equal to 0 stabilizes the feedback system, but obviously this is trivial and it's not interesting. So the strong stabilization problem becomes more interesting for unstable systems. And unstable systems are difficult to control. So this is the very famous Bode lectures given by Günther Stein in 1989. And he argues there, using Bode's integral properties, say integral formulas, saying that if the open loop plant transfer function contains right half plane poles, then what can be achieved in the sensitivity gets worse, okay? So for this reason, you don't want to introduce extra right half plane poles in the open loop transfer function. So use a stable controller if possible. Simple yet important examples of unstable systems are like the one shown here, which is an abstract model of an experimental X-29 aircraft. An example I mentioned before, but you also have other interesting problems. If you have two links like this, and then you try to stabilize, that's a acrobat problem. So they have two unstable poles and delays. Another important fact is the following. Even if your plant is stable, okay, let's say H equal to 1 and plant is a stable time delay system, and you want to do mixed sensitivity minimization in the sense of H infinity. So you want to find a controller, so stabilizing the feedback system and minimizing this H infinity norm. So W1 is the sensitivity weight, W2 is called the robustness weight or complementary sensitivity weight. So in this example, you see when K over A is large, you put more emphasis on W. So you want to minimize the sensitivity, okay? So K over A is large, what I call aggressive design. So you want fast tracking, you put a lot of emphasis on the performance of the feedback system, okay? So it turns out that if you do an optimization here, the optimal controller that you get is unstable below, above this dashed line and stable below this dashed line, okay? So the dashed line is, so K over A is the x-axis and logarithm of H is the y-axis. So when H and K over A both become large, the optimal controller becomes unstable. So you don't want to be very aggressive, okay, to start with. So why strong stabilization? So first of all, we have seen body integral constraints from Günther Stein's argument. Secondly, the controller is usually implemented in software. You develop algorithms and you write it in MATLAB, and then that gets put in a hardware, and then that is put in a box. Let's say there's an aircraft, and you give the implementer the software, the algorithm, the code, and then they come back to you and say, okay, here is your box, I implemented it, put it in the aircraft. Do you trust the person? I mean, what do you do? I mean, how do you check that? Of course, you have to check that this person has implemented it correctly. So what do you do? Offline open loop testing of the controller box, right? You apply some test signals and you look at the output. But if the controller is correctly implemented and you gave the person an unstable controller, that is impossible to do because in no time it blows up and you cannot test it. So for this reason, actually, the people who implement and put it in the aircraft, they are very reluctant to use unstable controls.
Could you review the definition of optimality here, of the optimal controller?
Okay. Yeah, okay. So one example is this mixed sensitivity minimization in the H infinity sense. But it is also true with the H2 controllers as well. So this is how actually I got interested in this problem. In 1994, I was at Ohio State, and I just got my tenure. I got promoted to associate professor. And then I received a phone call from NASA Lewis Research Center in Cleveland. And they asked me if I was interested in doing summer faculty fellowship at NASA on this topic. So I told them, what is the problem? And I mean, as long as feedback system is stable, there's no issue. But they gave me this argument, and they said they were using H2 and H infinity optimal controllers, LQGs, etc. Apparently they were being aggressive in the sense that, so the Qs and Rs that they were selecting, let's say, are very aggressive. So a lot of weight on Q, less weight in R, for example, would result in something like that in, state feedback plus observer design type of controllers. But it is true in H2 H infinity problems. So you get eventually an unstable controller.
And just to review the definition of optimality, the actual optimizability.
It's this one.
That one. That's it.
This is it. This is the optimum performance level.
Right.
Okay. So subject to feedback system stability, you want to minimize the infinity norm of this transfer function.
Right. Thanks.
Okay. But the H2 version also is the same.
Yeah.
It will lead to the same.
And just a clarification here, the result that this plot this is not a feature of time delay. This would happen even without time delay.
No, this is a function of time delay. So you see this y-axis is the time delay,
Okay.
and x-axis is the k over a. So how aggressive you are in your design. Okay. Okay, so these are two reasons. And the third reason, actually, which is also very compelling to use stable controllers, is that let's say your sensor is a network here. So the output goes to the controller side through a network, and somebody is messing up your network. Let's say there's a malicious attack that takes out the network. And suddenly you don't get anything in the measurement signal here. So then your system operates in open loop. So if you have an unstable controller, open loop system is unstable, and then you are doomed, right? So that's another important point. And the fourth reason is that simultaneous stabilization of two systems is equivalent to strong stabilization of an auxiliary system. Okay, so that's also important. So if you have a system which actually there are two possibilities for your actual physical system, and you want to stabilize both of them, but these are two discrete plants. And you do a strong stabilization for an auxiliary plant. And also, when you have a stable plant, it's relatively easy to approximate it. Okay, so that's another thing. Strong stabilization methods. Okay, let's talk a little bit about. So we already know how to stabilize a given plant, right? So if you have an nth order plant, you do observer plus state feedback, let's say, you get at most an nth order stabilizing controller. Okay, so that's relatively easy. And or you can do Lagrange interpolation, you can again get the same. But for strong stabilization, you need an extra condition to be able to solve this problem. So the extra condition is given by Euler Bongiorno rule, which is the parity interlacing property. So every pair of positive real axis zeros, you must have even number of poles. Okay? And the proof is not very difficult to see, actually. When you construct a unit, anyway, let's not go into the proof, but if this number is odd, then it means that the unit must change sign on the positive real axis. It means that it must have a zero on the real axis. Its inverse is not stable, okay? On the other hand, the other difficulty is the following. Even if the plant satisfies the parity interlacing property, you can find a strongest stabilizing controller, theoretically speaking. There may be some situations depending on the pole zero location. So location now plays an important role, not just the number of pole zeros. That the strongest stabilizing controller order may be extremely high. For example, in this configuration, there are complex conjugate zeros, and as the imaginary part goes to zero, the order of the strongly stabilizing controller goes to infinity. Okay, and as you can see, when they hit the real axis, parity interlacing property is being violated. Okay, because there will be like one hole. Okay, so there is a difficulty associated with this problem. One of the first algorithms was given by Euler and his colleagues. It is also repeated in Vidyasagar's book and Doyle Francis Tannenbaum book. I'm not going to go over the technical details of this algorithm, but you try to construct a unit in H infinity from the interpolation condition, these interpolation conditions. And they use small gain theorem and a sequential way of constructing the interpolating function. So an example here, so I have this example, a third order plant with a zero at 1 and 2, and also at infinity because this is strictly proper. And the right half plane poles are between 1 and 2, okay? So for this value, p equal to 1.2, I follow the algorithm and you get a 7th order strongly stabilizing controller, okay? So although you started with a third order plant, you have to go to 7th order in order to get the strongly stabilizing. And if you allow yourself infinite dimensional controllers, it's easier to solve this problem. So here it is. You can choose your unit as e to the f, okay? Where f is in H infinity and f is bounded in the right half plane, okay? So the interpolation conditions lead to Lagrange interpolation for the construction of f, okay? Here is the example. For the same example, f turns out to be a second order transfer function, but we are going to take e to the f, okay? So e to the f is my u, and you look at the magnitude of u inverse. By the way, u inverse is related to the magnitude of the sensitivity function. So it can be large at some values, okay? So because we only put a bound on the magnitude of u, we did not put a lower bound on that. So you can actually put a lower bound on the magnitude of u, and that means that you want your analytic function u to take certain specific values in the right half plane. So map this region, which is a simply connected domain, into unit disk, map the right half plane to unit disk, and you want to find a interpolating function from closed unit disk to unit disk, which is a Nevanlina peak problem. Again, it can be solved, okay? But the problem here is finding the conformal map, this one. You can check in Nehari's book. But that map is infinite dimensional, okay? So you are gonna get a finite dimensional function here, but going to the other side, you will have an infinite dimensional function. Okay, so that's something. Now, one of the criticism for the interpolating methods for controller design is that if I don't know these values exactly, so what happens? If there is a perturbation in the interpolation points, what happens? So in that case, you look at this problem, let's say if this is your true plant, your nominal plant is N over D, and the uncertainties are described by these numerator and denominator perturbations. Okay, let's say W1 and W2 are known stable transfer functions. Their magnitudes on the imaginary axis will tell me how much confidence I have or how much uncertainty there is. And these are normalized to 1. So you design a U starting from P0 N over D. You construct your strongly stabilizing controller that leads to S0 and T0. And if you look at the sensitivity function for the uncertain system with this C0, with this controller, it's this expression, and it is going to be stable by the small gain theorem if this norm is less than 1. Okay, so that brings us to a very interesting problem. So here you used a strongly stabilizing controller, stable controller. So what can be the minimum value at, in the left-hand side? What is the smallest value in the left-hand side if I give you plant W1 and W2 over all strongly stabilizing controllers? And that is currently an open problem, unknown. There are some bounds for it, but not known. The other approach is strong stabilization under sufficient conditions. So P is N over D. Now let's restrict D to have 1 at infinity. I can always do this. This is a normalization. So the value of D at infinity is 1. And I want to construct a unit U in this form. So if I choose W0, an arbitrary unit in H infinity, such that its value at infinity is also 1, then W0 times U is unitary in H infinity if and only if U is unitary in H infinity. So then let's look at W0 times U, which is this expression here. And it can be written as 1 minus R minus N times Q1, where Q1 is W0 times Q. And R here is 1 minus W0D. Okay. So by the, again, small gain theorem, if I can find a Q1 such that this norm can be less than 1, then I solve the problem. Okay, so that gives me my strongly stabilizing controller. But this is a sufficient condition only because I use the small gain theorem. And the left-hand side, okay, so this problem, minimizing the left-hand side, is a one-block H infinity problem. We know how to solve it, okay? Now, if you want to further impose a bound on the controller magnitude, so controller must be stable, but also its infinity norm must be less than, let's say, rho. So combined with the previous condition, it gives me a two-block H infinity problem to solve. And again, we know how to solve this problem. And so what we are going to do, we will be interested in solving this problem for systems with time delays. Okay, so I'll give examples of that.
Could you remark about the multivariable versions of this theory?
Yeah, exactly. It works exactly the same way. In fact, let's see, where is this? Ah, okay, right here. So there is, if this problem, okay, so the original version, which I wrote with my former PhD student, was the multivariable version. So I just wrote it in simplest terms here. Okay. So the other interesting thing here is that if the problem is solvable for some rho here, is rho 0, and then it is also solvable for rho greater than rho 0. So that allows us some kind of a parametrization for a set of strongly stabilizing controls. So there are other methods for strong stabilization method, but I'm not going to talk about them. So time delay systems. So we are going to apply the techniques that we have seen to time delay systems in the remaining 10 minutes or so. But before I do that, I would like to give a new result, which I'm very excited about, on control of time delay systems in general. So classical way of approaching the time delay system stabilization is Smith predictor structure, okay? So you have a nominal, a non-delayed plant P0 here and a delay here. So what you do typically is you design a controller K for P0. So the feedback system, if there was no delay with controller K and plant P0 would be stable, okay? Then you close the loop around K using this predictor feedback, okay? So that is the classical Smith predictor. So there are some robustness issues. What if you don't know, because there is a time delay here and the exact value of the time delay appears here. There is P0 here, there is the same P0 here, okay? So what happens if you don't know them exactly, okay? And also this approach works only for stable P0 or at most P0 that have poles at the origin, okay? Now, you can consider a set of unstable, uncertain plants in the set. The same technique applies, the same extension to Smith predictor applies. So you design a controller K for P0, which is the nominal plant here. And the resulting sensitivity, complementary sensitivity function is T0, okay? So for the non-delayed system, you construct a controller, step one. In step two, again, you close the loop around it like this. So this is nominal plant. This is the nominal time delay. But now you have a transfer function, a filter H here to be designed. And H is stable, and it satisfies these interpolation conditions here. And it satisfies an H infinity norm bound. So this is again back to Nevanlina peak interpolation. Okay. So in the nominal case, when the uncertainty is 0, so the transfer function you get from the reference to the output is again T0 times the delay, which is really the main idea of the Smith predictor. So that is the extension to unstable plants. So more general distributed parameters can be handled in this way. Instead of delay, you can have an arbitrary either function, but let's not. So this is a small extension of that. So okay, so that was stabilization. So how does it help? Does it help in strong stabilization? Okay. So in the for the strong stabilization, this C0 here has to be stable. Because I know H is stable, so this C0. So when is this guy stable? So even if when K is strongly stabilizing P0, that loop may not be stable. Okay, so that's a hard problem. It's one of the open problems. But the interpolation methods that I showed for the rational transfer functions, strong stabilization, applies to time delay systems. I'm going to show just one example of that. And the small gain method applies to time delay systems. I'll show you another example. So the first example, the interpolation methods. You can do a factorization of the plant. So this is your plant, quasi-polynomial divided by another quasi-polynomial. In order to do the right half plane poles and zeros, you have to find the roots of the numerator quasi-polynomial. So these are the roots. So these are right half plane zeros. and these are right half plane poles, the roots there. So in order to find the roots of quasi-polynomials, we use various softwares that are now, they exist. Okay, and you can write the plant in this form, P0 times P1, where P0 is finite dimensional and P1 is infinite dimensional, but it is invertible in H infinity. So, so this part can be ignored essentially because it can be inverted stably and put it inside the controller. So you only are interested in strongly stabilizing this, and you can apply the technique interpolation method we have seen. But if you approximate P1 in the controller implementation, then we also need another infinity norm bound condition for stability. So this is an example, and
I have a question regarding the former slide.
Yeah.
Where did the time delay go? I'm having a
time delay did not go anywhere. They are in N here.
Okay.
See, there is a D also here. And then they also defined the values of these alpha i's and beta i's. Yeah. Okay, so believe me, this is a good numerical example. Let me skip this, okay? Okay, so small gain condition. So I can apply the small gain condition that we have seen for time delay systems. So in the previous example, our N was finite dimensional, but now for time delay systems, your N will be infinite dimensional. It will contain a time delay, okay? So we will consider two problems here. SS0, given a plant, find a strongly stabilizing controller using this small gain theorem. And SS1, find a strongly stabilizing controller such that the weighted sensitivity is less than a specified value. Okay, so this is the example I take. You see here, there is a parameter H. So I'm going to leave this delay amount free, okay? So I'm going to see whether I can find a strongly stabilizing controller using the small gain technique for the values of H that are given. Okay, for which values of H I can find this solution. And the one block problem that you get out of it now becomes this. Okay, by the way, maybe I should go back and talk about this little p. Little p is the only root of the denominator here in the right half plane, and it is 0.58. So the plant satisfies the parity interlacing property because this is to the left of the 0, which is 4. Okay, and the other 0 is at infinity. So PIP is satisfied. And then you need to check whether this is less than 1 or not for the specific values of the delay, okay? And it turns out that this function gamma 0, depending on H, hits 1 exactly at H equal to 0.3377, okay? Now, we ask the next question is, let's say I give a rho, let's take rho equal to 2, okay? And weight W1 S plus 1 over 10S plus 1. And can we find a strongly stabilizing controller such that this condition is satisfied? And I apply the procedure again, one block problem. And it turns out that the one block problem is solvable for the values of H that are less than 0.13. So this is obviously an extra condition. So it restricts the values of the delay that you can use. Okay, so previously it was 0.3377. Now it is down to 0.1354. Again, this technique is sufficient condition based only. I don't even know. For example, it may be possible to have, again, the same thing, less than, so this condition may be satisfied for higher values of h, but using a different technique, okay? So the open research problems in this setting are H infinity optimal controllers restricted to small gain. That was strong stabilization, sorry. Approximation of H infinity functions using finite dimensional approximations or fixed order low order stable controllers. So these are all unsolved problems. Strong destabilizing controller from the extended Smith predictor. I don't know how to do that at this moment. And then you can also talk about extension to nonlinear systems. For example, Hammerstein-Wiener type of nonlinearities, I think can be handled in this setting. Okay, that's all I would like to say. And these are some of the people I have collaborated over the several years, like over the 30 years or so, on this topic.